Hey, welcome back. So we've been talking about the continuous time Fourier series and calculating it. Now, in reality, we don't really usually calculate these things. Um, we have computer programs that do this for us. Chips actually will do this for us. Um, but nevertheless, it's important to see how these things are calculated for basic shapes like square waves and triangle waves and basic mathematical formulas like the shark fin, uh, 1 minus e to the negative t over tau, and then it comes back down. What we usually do is we have some sort of periodic signal, and we want to manipulate its frequency content somehow. So we do something in the time domain, and we adjust it in the time domain, and then it has some sort of corresponding effect in the frequency domain on the Fourier series. So there are these properties that we have to discuss. We do one thing in time and it has a corresponding operation in frequency. So let us start to begin identifying these properties. So I'm not going to prove a lot of these things. I will just cite you to the textbook, or Wikipedia is actually pretty decent when it comes to this. I will prove the first couple and then we'll just discuss the rest of them. It's not a good use of our time to prove all of these things. So I will prove the first few just so you can get a flavor of how the proofs go. So I'm going to prove linearity, and linearity goes like this. Suppose x and y are each periodic with period t, maybe not necessarily the fundamental period. And suppose x of t has Fourier series coefficients ak, so I'm using this notation, this arrow with fs. So x of t has Fourier series coefficients ak, and y of t has Fourier series coefficients bk. Why bk? Well, we used ak for x, so we're going to use bk for y. Then maybe we want to know what are the Fourier series coefficients of alpha times x of t plus beta times y of t, where alpha and beta are constant, possibly complex constants. So this is called a linear combination. We have maybe 0.5 x of t plus 3 times y of t. We have a mixture now of these two signals whose Fourier series we know. What are going to be the Fourier series coefficients of this new mixture? All right, so to be able to figure that out, we start from the definition of the Fourier series. So first of all, if we have a weighted sum of x of t and y of t, then this weighted sum will also be periodic with period t. And so if I want to find its Fourier series, I just plug it into the equation, the definition of the Fourier series. So this is the signal in parentheses whose Fourier series I want to analyze. And I could put 2 pi over t here, or I could put omega 0 there. So for brevity, I'll put omega 0. Okay, so I got this. And now, from the properties of integration, I can split this up into two integrals, right? Plus 1 over t integral over t beta times y of t e to the minus jk omega 0 t dt. And then I can even bring the alpha out, right? Bring the alpha out. And I can do the same thing over here. I can bring the beta out because it's constant. Same with alpha. Now I look at those two integrals. I've got alpha times this first integral. But what is that first integral? Well, go back to the definition of the Fourier series. That's nothing but the Fourier series coefficients of this thing, x, right? X of t. So, and we said at the beginning of this that x of t has Fourier series coefficients ak. So that first term is alpha times ak. And then if you look at the second integral, It's the Fourier series coefficients of y of t. So this is beta times bk. All right, and so we conclude that if you know x Fourier series and y Fourier series, and you put a mixture of, or if you have a signal that's a mixture, a weighted mixture of those x and y's, then the Fourier series coefficients of your mixture is the same mixture of Fourier series coefficients. That's the linearity property of Fourier series. So let's move on to the time shift. Again, suppose x of t, and we'll just write, we'll say is periodic with period t, and x of t has Fourier series coefficients ak. All right. Now we want to find out what are the Fourier series coefficients of x of t shifted. So x of t minus t0. And notice if x of t is periodic with period t, and if we shift it, it's still periodic with period t. So it still has a Fourier series, but we're going to shift it, and we want to know what is this thing's Fourier series coefficients. Okay, we'll call those Fourier series coefficients bk. Why? Because we already used ak for x of t. So we want to know how are the bk's related to the ak's. All right, so we go again to the definition. I guess we'll go to the bk. We'll say bk equals 1 over t integral over t times x of t minus t0, right? Because that's the signal whose Fourier series we want. E to the minus jk omega 0 t dt. Right? Now, I'm gonna pull a trick here called change in variables. I'm gonna call this a dummy variable. I'm gonna pick something other than t, usually tau, and I'm gonna let tau equal t minus t0. The idea is that I want to use the analysis equation, the definition of the Fourier series, to analyze x of t. But right now I have t minus t0, and the analysis equation just says x of t. So I'm going to put this dummy variable in for x of t minus t0, and then what we have, integral over t, x of tau, right? So now that matches, you can call t or tau or whatever, but that starts to match the analysis equation. And then to complete the change in variables, I have to substitute this t, and if I let tau equal t minus t0 and I solve that for t, then t is equal to tau plus t0. So this becomes e to the minus jk omega 0 tau plus t0, right? And then the dt, if I take the derivative of this little equation that I made, then I have dt equals d tau, because the t0 is a constant. So I can just put d tau here, and now I've changed the variables from t to tau. Now I can use a property of exponents, break this down. This is e to the minus jk omega 0 times t0 that I can bring out because that's a constant. E to the minus jk omega 0 t0, right? That does not depend on tau, so I can bring that out. 1 over t times the integral of t x of tau e to the minus jk omega 0 tau d tau. So what is this? Well, all right, I've got this constant here, e to the minus jk omega 0 t0, and then I look at this constant, or I look at what's multiplying the constant, 1 over t times the integral over t x of tau, and I compare this to the analysis equation, and it's exactly the analysis equation. It's just that the t's now I'm calling tau. right? But you integrate over that, and so they go away anyway. So this is nothing but the AKs. And so I've got this relationship here, that our new Fourier series coefficients are the old Fourier series coefficients multiplied by this e to the minus jk omega 0 t0. So let's be concrete about this. If I delay x by, let's say, 2 units, then my new Fourier series coefficients are e to the minus j2 k omega 0 ak, or 3, or whatever I delay. That delay shows up here in this constant. Now, about that constant, something interesting here. This is the constant I'm referring to. What's the magnitude of that constant? Well, for any k, for any omega 0, and for any t0, the magnitude of that is 1. This is an exponential form, and the magnitude is the number that multiplies. So that's a 1. So the magnitude is 1, and this thing has a phase, of course. The phase depends on k, omega 0, and t0. So what this is telling us is that delaying the signal does not change the magnitude of the Fourier series coefficients. Delaying the signal or shifting the signal only changes the phase of the Fourier series coefficients. But that's exactly what we think about when we delay a signal, or when we shift a sine wave around, right? When we shift that around, we haven't changed the shape of the sine wave, or we haven't changed how fast it oscillates. All we're doing is we're changing the phase of it. So this is perfectly in line with our intuition, what our intuition says about how a time shift changes that sine wave. It changes the phase. Okay, so hopefully this gives you a little bit about how these proofs, how we can get these proofs, all right? But I'm not going to prove these next 3. I'm just going to talk a little bit about them. So time reversal says that if x of t has Fourier series coefficients ak, then x of minus t has Fourier series coefficients a of minus k. So this means that if I flip the signal in time, then its Fourier series also flips. And so there's an important consequence to this. If x of t is even, that means when I flip it, it doesn't change. Well, then that means the Fourier series coefficients are also even. Okay? And if x of t is odd, that means the Fourier series coefficients are also odd. It has the same symmetry as x of t. Interesting. Now, the time scaling property says that, well, remember from the synthesis equation, if x of t has Fourier series coefficients ak, then I can synthesize x of t like this. Right? If x of t has Fourier ingredients, right, Fourier series coefficients, here's the recipe or the ingredients, then I can add all these harmonics together to get back x of t. Well, if I scale it, scale the time, that is, by some constant alpha, that means, right, then I put the alpha up here in the power, and I'm going to group it with the omega, like that. So what this is telling us is that the AKs don't actually change. The AKs are the same. What changes is the Fourier series representation. The frequency changes, right? But the constants don't change. The fundamental frequency changes, and that makes sense. So if alpha was 2, that would be contracted by a factor of 2, so that means it goes up and down twice as fast. So that means the fundamental frequency is 2 times what it was initially, but the amount of that harmonic stays the same. Interesting. Okay, finally, for this video, but we're going to make a continuous time Fourier series properties 2. For this video, lastly, we can say again, suppose x of t has Fourier series coefficients AK and y of t has Fourier series coefficients bk. And of course, implied here is that they're both periodic with period t. Then the multiplication of the two of those has Fourier series AK convolved with BK, believe it or not. So again, the proof you can see your textbook or the Wikipedia, but yes, when we multiply in time, see the time operation of multiplication is the convolution in frequency. So this is a very important property, especially for communications. Okay, so that's it for the properties in this video, and we're just going to kind of move on to the next video for some more properties. Stay tuned.